company named Processor Technology was a major player in the early days of the microcomputer revolution. They're probably the most famous for a computer they made, the one you see here called the Sol-20. And this computer, with its integrated keyboard, integrated video, and a sleek low-profile case, was quite a departure from the computers of the day. The MSI and Altair, for example, which in addition to being boxy also required an external terminal, whether it was a video terminal or possibly a teletype. So to have it all integrated into this slick-looking package was quite a change. And the design of this computer greatly influenced numerous personal and home computers that would follow. I mean, of course, you can see this influence in the design of the Apple II computer. You can see it in the TRS-80 computers. You can see it in the Commodore 64, for example, the layout of the TI-99, the Atari 800 and 400 computers. It's in the NSX line of computers. You can see it in the Ohio Scientific computers, and on and on. So it became a very copied design style in the coming decade or so for personal and home computers. However, processor technology made an impact prior to the Sol-20 even, when they were just making hardware, mainly boards, for the Altair and MSI computer. They got their start making a 4K RAM board for the Altair. And this board sold very well. And it was the right price, and it actually worked, unlike Altair's own 4K board, which was just an absolute reliability nightmare for them. In fact, there's stories that at one of the first big trade shows, they had to use processor technology RAM boards, MITS did, to make their booth functional through the show. Now, with the success of that first RAM board, they went on to make numerous other boards for the Altair and MSI and other early computers. Probably their most influential was this video board here, the VDM1 video board. This was the first video board ever made for a personal computer. And with this board and a simple parallel keyboard, your computer could serve as its own video console. And at this point in history, where a video terminal or a teletype easily costs 2 to 3 times the price of your own computer, this was a huge price savings. Greatly lowered the barrier of entry into getting yourself a personal computer. So you can see what an impact this had. In addition, now you've got the video RAM on the bus with the 8080 processor. So you can update video several orders of magnitude faster than you could possibly do it through a serial port. What this means is you can now have graphics and animation and games that could never have been done with an external terminal. And of course, that had great appeal to the personal and home computer market as well. Now, the video board you're looking at is actually a modern reproduction of the VDM1. It uses the exact same schematic, has the exact same part designators. The only difference is that it's been relaid out using modern tools to fix some layout problems the original board had. The original board was laid out by hand with tape, and they got stuck by the end, and they ended up having to run an 8-conductor ribbon cable to get signals from this side of the board over to this side of the board that just kind of dangled across the front. So this layout gets rid of that problem, and also for convenience sake added a connector for video up here, whereas the original board you soldered the coax straight to the board, so you were forever tethered to that when you wanted to pull it out and move it around. So this just makes it more convenient, and it's a cleaner layout. So if you want a VDM1 video board, this is a great way to go. These are still available. You can buy them and build it yourself. I put a link to where you can get one of these boards in the description of this video. In the early days, before floppy drives were available for the microcomputer, there were 2 main options for mass storage. One would be to use a teletype as your operator console. Then you could use the paper tape reader and punch to load and save programs. Or if you were using a video terminal, then you typically went with a cassette interface option, which was usually a board in the computer, and then it connected to a standard cassette player like you see here, and just used inexpensive audio cassettes. Now, since processor technology had developed this video board, the VDM1, what they felt the world needed was a new and improved cassette interface. And that's the board you see here. This is the CUTS board from Processor Technology. CUT stood for Computer User Tape System. Now this board was definitely a jump ahead of what everybody else was doing at the time. To begin with, it did support the existing 300 baud standard that most people were implementing, but then it added a number of improvements. Number one, it was the first board to use an AGC in the read circuit. This meant that it was much less sensitive to the record level, to the playback volume setting. If there was dropouts or fades in the tape playback at all, it could handle that better as well. So it made that more reliable. It also provided two cassette interfaces here for two cassette players, including motor control of those cassette players. So this could read from one tape deck, turning it on and off as needed, and write to the other tape deck as it processed data, turning it on and off as needed. This is very analogous to what mainframe computers were still doing at the time with batch processing. And this is a way computers could handle huge database updates with just a very limited amount of memory. And of course, that's the situation we're in here with early computers. You have large amounts of data, for example, a large text file or a program you need to assemble that's bigger than the small amount of RAM. This two tape deck system allowed you to do that. But probably the most important feature this new board added was the fact that they added a 1200 baud interface for the tape instead of the 300 baud that everybody else was using. So this is 4 times faster than all the other cassette interfaces out there, 12 times faster than paper tape. So loading BASIC that used to take 8 minutes or 4 minutes, depending on what you were loading, now you're loading in under a minute. You can see what an improvement that was and why that was a desirable thing to have. Now, you take a look at these boards, you buy a new computer, and then you turn around, you could buy RAM that was reliable and good price from Processor Technology. You could buy this video board and get yourself a console for really cheap. And you could buy this cassette interface, and you've got your mass storage. By filling your computer with these boards from Processor Technology, your MSI or your Altair was a notch above what it could be if you had bought those same type of boards from MSI or Altair. So this was a big hit for Processor Technology. But they didn't stop there. They also decided to provide a tape operating system with this in order to make this all work together even more seamlessly. Let's talk about that next. With this background information about Processor Technology and the boards they made, now we can move on to the actual subject of this video, which is resurrecting a lost tape operating system. And as you might have guessed, the OS I'm referring to is the one that Processor Technology created for their VDM1 and CUTS interface boards. Now, they called this little OS the Computer User's Tape Executive, and it was designed to load and run up in high RAM on your system. However, at this point in history, the amount of RAM somebody might have in their system could vary substantially. RAM was still very expensive at this point, so it would not be unusual for somebody to have just 8K in their system, or maybe 16K. Then again, somebody with some money might have splurged for 32 or 48K. So what this means is that Processor Technology needed a way to load this operating system into a variety of different spots without having to create custom tapes for everybody. So what they made was a boot tape that allowed the user to specify the load address here on these send switches. And during the load process, it would relocate the executive, including changing address references, etc., as it moved it to the address range specified by the user on the front panel. This was a pretty slick solution. And as you might have guessed, it's this boot tape that is missing that I'd like to resurrect as part of this project. Now, fortunately, we are not starting from scratch on this. The bootstrap loader that you would toggle in on the front panel to get this process started, just like with Altair software, that is present in the manual for this executive, and we have that manual archive. So we have the bootstrap loader to get it started. We also have a dump of the executive. It was available in ROM up at C1000. So we have that to start with as well. Now the reason that's available in ROM is because Processor Technology made one more board for this set. They called it the GPM board, General Purpose Memory. And it included sockets to put this executive in ROM, and it also included the 1K of RAM that the executive needed. Now it had a number of other features as well, but in the end, this was the more common way for this executive to be distributed. So that's why the ROMs were available. Plus, yeah, the ROMs tend to not lose their code as easily as an old cassette tape might. All right, so given the executive code, given the bootstrap loader, that just really leads us to have to develop or reverse engineer how they might have done the actual relocating loader that's on the tape that takes CUTER, modifies all the addresses as needed to match what the user specified on the front panel switches, and then sticks it where the user asked us to put it. So that will be the job for the rest of this project. All right, now on a quick side note, when this OS became available in ROM, its name changed slightly. It now became the Computer User's Tape Executive ROM. And the acronym for that is CUTER when you say it. And that sounded a lot better than CUTE. So CUTER is the name that stuck for this little tape operating system. And when I say CUTER, your ears might have perked up because you've heard of this before. You might have seen me use it in several of my videos. And you've heard me refer to it as a monitor. And yes, it is in ROM and it has monitor-like functions, and that's mainly what I used. But in reality, it's more operating system-like than, for example, North Star DOS or most of the very first generation disk operating systems that had hardware abstraction for tape access, it had hardware abstraction for I/O ports, more OS-like than, again, something like North Star DOS was. And we're going to demonstrate some of that in just a minute. Now, I was going to go through the process of how I created this bootloader, but I think what I'll do first is go ahead and let's just boot this up and see it all work, because right now this video has just been a lot of talk and very little action, and we got to get some demos going here to keep this video a little more interesting. Let's take a look at the hardware we're going to use for this demonstration real quickly. We've got a total of 16K of RAM in this system. It's all on this one board. This is a Processor Technology 16K RAM board. Next to that, we have the Processor Technology VDM1 board. That's our video board for console output. And then the CUTS board that we showed you, that is the mass storage we're going to use with cassette tape. And then lastly, I have a combo parallel serial interface board that is hooked to our keyboard for console input. Now, normally that would be the 3P plus S board made by Processor Technology. However, I don't have the 3P plus S, so I've configured a solid-state music IO4 board to look exactly like the 3P plus S as far as software sees it. So CUTER thinks it's using a 3P plus S board. So this group of boards together would be what a lot of people would buy and stick in their Altair to get this added functionality that Processor Technology is providing. And they called this group of boards Subsystem B. There was some variety to what you could put into that. For example, when the GPM board that houses the CUTER in a ROM at C1000 came along, that was part of Subsystem B as well as CUTER itself would be considered part of Subsystem B. Now, interestingly, the hardware and software that made Subsystem B was combined onto a single large board and became the heart of the SOL20 computer that I showed you at the beginning. Everything but the large RAM boards, like the 4K, 16K RAM boards, those would still just plug into your S100 expansion bus in the SOL20. But the main motherboard had the video on it, it had the cassette interface on it, it had the keyboard interface on it, obviously already. It had the RAM that CUTER required, it had a spot for the CUTER ROM, etc., etc. So anyway, because they're so similar, what would run on the SOL20 would also run in an Altair with a Subsystem B and vice versa. And we'll demonstrate that in just a minute. All right, let me put the cover on this so I can get the video monitor in view, and we'll go ahead and start the boot process. In the early days of the Altair and MSI computers, if you wanted to load a program from paper tape or cassette, the first thing you had to do was enter a bootstrap loader here on the front panel in order to give it enough smarts to begin reading that paper tape or cassette device. And that bootstrap code was typically provided in the manual for BASIC, or for example in this case, for this CUTER tape we want to load. Here's the cassette loader, bootstrap loader right here. It starts at address 0. Now you can see these are all in hexadecimal, whereas the Altair was designed for octal entry on the front panel. And this was not an unusual problem for hobbyists of the day, because a lot of them would prefer to work in hexadecimal anyway. It's just a more convenient numbering system for an 8-bit processor. So you'd see things like this, where you put marks between groups of 4, or you might go ahead and use different colored switch caps here. You do 4 here and then another color here to group in groups of 4 for hexadecimal. All right, I'm going to enter a few bytes here. I won't make you watch the whole thing. We'll put a couple in and then do a video cut while I do the rest. All right, this needs to start at address 0. The easiest way to do that is to do a reset. Now we're loading at 0. The first byte is a hex 21. We'll deposit that at 0. The next byte is a hex 40, and now we can use deposit next from now on. Next byte 0. And let's do one more, it's F9. All right, and then we'll just complete that procedure and get the rest of this bootstrap in and come back and finish. All right, so I have that bootstrap loader entered through the front panel. It's going to run from address 0, so I need to set to address 0 on the front panel. Easiest way is a reset. Now I'll be running from 0. But before we hit run, we need to tell the loader on tape where to put CUTER in memory. We want it up at the top of our RAM. We have 16K of RAM, so we want to be just below that 4000 hex boundary. CUTER itself needs 2K, and then it wants 1K of RAM after itself for its scratch pad use. So a total of 3K RAM is needed up there at the top of this 16K board. Take 4000, come down to 3K, that puts us at 3400. So here on the 8-cent switches, we specify that page address, 3400, and now the loader will know where to put CUTER. All right, we can go ahead and hit run at this point. But you look over here, you'll see I've already got play on the tape player pressed, but the tape is not running, and that's because we have motor control. So when I hit start, it's going to automatically start the motor for me as the program starts running. It's kind of handy. And then when it's done loading, it's going to automatically stop the tape for us as well. All right, so you'll see, well, the light pattern just changed. I missed that explanation. Basically, one light pattern was visible as it was loading the loader off of tape. Once the loader started running, you could see it change slightly, at which point it's actually loading CUTER. Once it gets CUTER loaded, it's going to execute a halt instruction, actually an 8080 halt instruction. You'll see all the lights come on, and the computer just stops at that point. There we go. It stopped. Now, the reason it did that rather than jumping straight into CUTER is because there's some switches we need to set on the front panel to tell CUTER what type of I/O devices we're using for console and things. All right, now if you look over here, you'll see it automatically stop the tape for us as well. All right, so the only way to exit a halt state on an 8080 is to do a reset. And if I do a reset, it's going to jump back to address 0 and start running, not to 3400 where we loaded CUTER. So to get around this problem, or just to save you a step when you're doing this normally, this load process automatically puts a jump at address 0 to wherever it loaded CUTER. So frankly, all I have to do is hit reset and it'll start running CUTER for us. Now, but before we do that, it halted so that we could set these lower 4 switches to the proper values for our output device and our input device for the console. We want it to go to this video display from the video board. That's these 2 switches. 0, 0 is the video display. Those 2 are already correct. These 2 determine where your keyboard is coming from. We want it to come from an external serial port using a serial keyboard that I've got. The value for that is 0, 1. So coincidentally, it happens to be correct already. If it was a parallel keyboard, you put in 0, 0, but we want 0, 1. All right, so if I hit reset, we should come up and run with everything set like I need. All right, and there you go. You can see we've got the CUTER prompt at the top. That's that caret. Let's see if I can get that in view. All right, this has typical monitor commands like you're used to, of course. I've demonstrated some of these. We can dump a range of memory, say 0 to 20 hex. We can enter values starting at an address, say enter at 0. We'll put in 0, 1, 2, 3, 4, 5. Terminates with a /. So now if you look at 0 to 20, you can see we've got the data we entered, 0, 1, 2, 3, 4, 5. All right, commands to load a program from tape. You can do a get, and that would load a program by file name. You can do a save, that would save it by file name. You can execute a program by file name. So we could execute a program called target. This is going to automatically start the tape and go out and look for target. You can see down here the tape is already running. Now, if I had fast forwarded that to where target was on the tape, it would be a little quicker, but it is the next item on tape, so it should find it quickly. Anyway, and I can go off and get a cup of coffee and come back and this will be done. Now, what's interesting is this target program, you've seen me run it on different configurations. I've run it on the Sol 20. I've run it in this Altair with the CUTER in ROM at C1000. Here I'm going to run it with CUTER in RAM at 3400. And yet none of this has changed. It's the same CUTER. It's the same target program. None of it had to be recompiled or reassembled. So that's pretty slick, and that is the beauty of the Subsystem B and its operating system-like characteristics. As long as the programs play by the rule, they're very portable. And I'll show this even a further demo in just a minute when I load BASIC. All right, you might have seen this program before. Let me just put it into demo mode. Well, actually, I'll go ahead and run it. If you were playing games in BASIC, like craps or whatever, and then you got this on your computer where it's a nice shoot 'em up game, it gives you an idea of what you can do with a video board as opposed to a terminal. And you might have seen this in other videos where I actually had an AM radio on and you could hear the sound effects it generated just coincidentally by the fact that there's interference, but they actually kind of went with the game. The explosions made different noises and the ships going by made noises. All right, so you get the idea, but This is definitely a notch above anything you could do on a serial terminal, of course, or a teletype. So I hit escape and I'm out of the program. I'm at the CUTER prompt right now. All right, what I'd like to show you next though is how powerful this pseudoport concept, the logical ports are on this, by starting this over again and just simply changing these front panel switches to use a different device for input and output. So I'll need to hook this up to a terminal and we'll show you how that works. Let's say you already had a video terminal like the one you see here on the right, and you didn't want to buy a VDM1 video board. You just wanted to buy the CUTS board, the cassette interface board, because it was nice and fast, and then you wanted CUTER to run everything. This way you could still use all this to run, let's call them normal programs that don't require the video board, like BASIC and stuff like that. Well, without any changes, it could support this configuration as well, just to show you how powerful this simple system is. All right, I've already entered a bootstrap loader on here. I already set the switches to 3400. So we can go ahead and just hit run, and this will load CUTER just like we did before. Except this time, when it halts, instead of putting in 00 to specify the VDM1 for output, we're going to put in 01 to specify a serial port. Likewise, for the input device, we also want that to be a serial port, so we'll specify 01. So as soon as it's halts, we'll go ahead and do that. Then all we'll have to do is hit reset, and off and running it'll go, and it should work on the video terminal. It should finish. All right, so that's finished. So we put 01 for serial port output, 01 for serial port input, hit reset. Watch the terminal over there on the right. You should see the prompt come up. There it is. So now we've got CUTER running on our video terminal, just like that. Again, no changes in software or hardware, really anything, just very flexible. And so you can see we're here in CUTER, we could do a dump or something like that. And we can also run a program off a tape. Let's go ahead and load BASIC. So we go ahead and load BASIC. It'll run just fine on this video terminal. Again, it just takes about a minute to load this, nice and quick. I'll do a video cut and we'll come back when this is done. All right, so that finished loading. It's up and running, and you can see we got the ready prompt here in BASIC. We can print 2 plus 2, typical things like I always do. We do our little for loop test. Well, anyway, you've seen that stuff a million times. You don't need me to do that again. But again, I just wanted to show you how quickly you could come up with another configuration without really having to change anything. We can get back to CUTER with a buy, and you can see we're back in CUTER. All right, so that does it for the demonstrations. I really like this system. It was impressive back in the day. They had obviously put some thought into their hardware and their software designs in order to make it this flexible and a little more, let's call it professional, than some of the other early designs back in the first days of the Altair and the MSI. At this point in the video, I was going to go into the process of how I created the relocating bootloader and made the tape. But this video has already gotten very long, so I think that's going to be a bit too much. I may do another video where I follow up on that, but in the meantime, I've put links to the actual code I wrote for the bootloader that is on the tape that does the relocating. You can take a look at that. But I think I'm going to have to give this video a rest for now.